What if the universe isn't just vast but holds mysteries so profound they could completely rewrite everything we think we know about reality? From invisible forces shaping galaxies to stars behaving as though they have no business existing, the cosmos is a treasure chest of wonders that defy logic and challenge our understanding of existence itself. In this video, we're diving into 30 of the most mind-bending discoveries that leave even the brightest minds baffled. Have you ever wondered why entire galaxies are being drawn toward an unknown force, or how a single star could appear older than the universe itself? Keep watching as we unravel secrets so extraordinary, they might just make you question the very fabric of reality. Buckle up, because this journey through the cosmos is going to stretch your imagination to its absolute limits. Now turning to the first discovery, let us uncover the enigma of the Great Attractor. Imagine a gravitational force so immense that it's pulling entire galaxies, including our own Milky Way, toward it at unimaginable speeds of hundreds of miles per second. This region of space, located roughly 150 million light-years away, is shrouded in mystery. Scientists have identified its presence through the movement of galaxies, but what exactly lies at its heart remains unknown. When we gaze in its direction, our view is blocked by dense clouds of gas and dust in the Milky Way, making it incredibly challenging to study. What we do know is that its gravitational pull suggests an incomprehensible amount of mass, possibly a supercluster of galaxies or something even more unfathomable. Yet, its very existence challenges our understanding of how cosmic structures form and behave. How can something this massive exist in relative secrecy within the cosmic fabric? While some theories suggest it could be a vast concentration of dark matter, we are left with more questions than answers, a testament to the universe's ability to keep its most profound secrets hidden. Moving forward, we'll dive into another cosmic curiosity that raises just as many puzzling questions. Now turning to the second discovery, let us unravel the mystery of the cosmic microwave background cold spot. This region in the faint afterglow of the Big Bang, the cosmic microwave background, is noticeably colder than its surroundings, and that anomaly has left scientists scratching their heads. Discovered through detailed measurements of this ancient radiation, the cold spot is not just a small curiosity, but an expansive area spanning billions of light years. One leading theory suggests that it could be caused by a supervoid, a massive and nearly empty region of space containing significantly fewer galaxies than expected. As light travels through such a vast void, it loses energy, creating the illusion of a colder patch when observed from Earth. However, what makes this even more perplexing is that the cold spot seems far too pronounced to be fully explained by a supervoid alone. This has led to more speculative ideas, including the tantalizing possibility of alternate universes. Some scientists have proposed that the cold spot could be evidence of a collision between our universe and another, leaving a faint but enduring imprint on the cosmic microwave background. If this hypothesis holds any truth, it would fundamentally reshape our understanding of reality itself. Yet, like so many cosmic mysteries, definitive answers remain elusive. Is the cold spot merely an extraordinary coincidence within a supervoid, or could it truly be a window into a multiverse far beyond our comprehension? As researchers continue to investigate, the intrigue surrounding this chilling enigma persists. Moving forward, we'll venture into another puzzling phenomenon, one that reveals an even deeper cosmic mystery. Now turning to the third discovery, let us explore the profound enigma of dark energy, a force so mysterious that it fundamentally challenges our understanding of the universe. Discovered in the late 1990s, dark energy emerged from observations of distant supernova, which revealed that the universe is not only expanding but doing so at an accelerating pace. This was a shocking revelation, as gravity was expected to slow down the expansion over time, not speed it up, scientists theorized that an unseen force, now referred to as dark energy, must be driving this cosmic acceleration. Astonishingly, dark energy is thought to account for nearly 70% of the total energy in the universe, yet its exact nature remains one of the greatest unsolved mysteries in modern physics. Is it a property of space itself, as suggested by Albert Einstein's cosmological constant, or is it something entirely different, like a dynamic energy field permeating the cosmos? Adding to the puzzle, the effects of dark energy appear to grow stronger as the universe expands, a phenomenon that defies intuitive understanding. While its existence is indirectly confirmed through its impact on the cosmos, dark energy cannot be directly observed, leaving researchers grappling with its fundamental essence. Unraveling this mystery could lead to groundbreaking advances in physics, reshaping everything we know about the universe's origins, structure, and ultimate fate. Could dark energy be the key to understanding the fabric of reality itself, or will it remain an eternal enigma? As we ponder this profound question, we turn to the next cosmic discovery, one that brings us closer to the edge of interstellar intrigue. Now turning to the fourth discovery, we encounter the captivating mystery of Oumuamua, the first known interstellar object to pass through our solar system. Discovered in October 2017, this peculiar visitor immediately puzzled astronomers with its unusual characteristics. Unlike any comet or asteroid previously observed, Oumuamua's elongated, cigar-like shape defies conventional expectations. Measuring roughly 800 meters in length but only about 80 meters wide, it resembles nothing naturally formed within our solar system. Even more intriguing was its motion. As it traveled through space, Oumuamua exhibited a slight acceleration that could not be fully explained by gravitational forces alone. Typically, comets achieve such changes in speed due to outgassing, where jets of gas escape as they approach the sun. However, Oumuamua showed no visible signs of a cometary tail or such activity, deepening the enigma. This has led to a range of theories attempting to explain its origin and behavior. Some suggest it is a natural fragment from another star system, possibly ejected after a collision. Others propose it might be an entirely new category of cosmic object, unlike anything we have encountered before. Perhaps most controversially, a small but vocal group of scientists has raised the possibility that Oumuamua could be an artificial object, potentially a probe or spacecraft from an alien civilization. The lack of conclusive evidence leaves every possibility on the table, making Oumuamua a focal point for scientific debate and imagination. What makes this discovery even more intriguing is that it may hint at countless other interstellar objects passing through our solar system undetected, each carrying with it the secrets of its origin. As we reflect on the mysteries of Oumuamua, we move to the next discovery, one that takes us from the cosmic unknown to a star whose behavior challenges even the brightest minds in astronomy. Moving forward, we arrive at the fifth discovery, the perplexing case of Tabby's star, officially known as KIC 8462852. Located around 1,500 light-years from Earth, this star captivated astronomers due to its highly unusual and unpredictable dimming patterns. Unlike typical stars that exhibit consistent brightness or predictable variations, Tabby's star has been observed dimming by up to 22% at irregular intervals, a phenomenon that defies conventional celestial behavior. What makes this even more mystifying is that these fluctuations occur without the periodicity seen in other stars with orbiting planets or debris. Initially, scientists hypothesized that a swarm of comets or a dense dust cloud might be blocking the star's light. However, follow-up studies failed to find conclusive evidence supporting these theories. Adding to the intrigue, the dimming occurs across a wide range of wavelengths, suggesting that dust alone cannot fully explain the phenomenon. This opened the door to more unconventional ideas. Perhaps the most attention-grabbing of these is the speculation about alien megastructures, such as a Dyson sphere, a hypothetical construct designed by an advanced civilization to harness a star's energy. While this idea has sparked widespread curiosity, it remains a fringe theory with no concrete evidence to support it. In recent years, more refined observations have suggested that the dimming might be caused by natural, yet still unexplained, phenomena related to the star's activity or surrounding environment. Despite extensive scientific investigations, the true cause of this bizarre dimming pattern remains elusive, keeping Tabby's star at the center of ongoing debate and fascination. Unlike anything we've encountered in our exploration of the cosmos, this star challenges our understanding of stellar behavior and reminds us how much we have yet to learn. As the mystery of Tabby's star endures, we turn to a question that has haunted humanity for generations. Why have we yet to see evidence of other intelligent life in the vastness of the universe? As the next challenge unfolds, we encounter the enigmatic Fermi Paradox, a question so profound it cuts to the core of humanity's quest for understanding. If the universe is so vast, teeming with billions of galaxies and countless planets, then where is everyone? Why have we not yet found evidence of other intelligent life forms? This paradox, named after the physicist Enrico Fermi, highlights the stark contrast between the high probability of extraterrestrial civilizations existing and the complete lack of communication or observation of them. The numbers alone are staggering. Among the estimated hundreds of billions of stars in our galaxy alone, many should host planets in the habitable zone. Even if only a fraction of these planets developed life and an even smaller fraction evolved intelligent beings, the galaxy should still, in theory, be bustling with activity. Yet the silence is deafening. Why? Scientists have proposed several potential explanations, each as fascinating as it is unsettling. One idea is that intelligent civilizations may self-destruct before they reach a stage where interstellar communication or travel is possible, a sobering possibility known as the Great Filter. Others suggest that advanced civilizations might intentionally avoid contact, either for self-preservation or to follow some form of cosmic ethics, leaving us in the dark. There is also the unsettling hypothesis that we might be missing their signals altogether, either because they use technologies far beyond our comprehension or because we are simply not looking in the right way. Alternatively, we may be truly alone, a possibility that challenges not just our scientific understanding, but also our philosophical and existential beliefs. The Fermi Paradox does not just question our place in the cosmos, it highlights the limits of our knowledge and forces us to confront the vast unknown. As we ponder this persistent mystery, we move to another cosmic anomaly that challenges the very principles of physics itself. Moving forward, we encounter the baffling Pioneer anomaly, a mystery that continues to perplex scientists even decades after its discovery. Pioneer 10 and Pioneer 11, two spacecraft launched in the early 1970s to explore the outer planets, should have followed predictable paths as they ventured further into the far reaches of our solar system. Yet, to the astonishment of researchers, both probes began exhibiting an unexpected and subtle deceleration, as if some unseen force was tugging at them ever so slightly. At first, this deviation seemed minuscule, almost negligible, but as data accumulated over the years, it became evident that this was no random glitch. Something significant was at play. Scientists pored over every possible explanation, meticulously analyzing factors like the spacecraft's thermal emissions, the influence of solar radiation, and even the gravitational pull of distant celestial bodies. While thermal radiation leaking from the probes was proposed as a partial answer, it could not fully account for the anomaly observed. The exact cause remained elusive, leaving room for speculation about unknown forces or phenomena at work. Could there be a hidden variable in the fabric of space-time itself, or perhaps an entirely new force of nature yet to be discovered? This enigma not only deepens our curiosity, but also serves as a humbling reminder that even in the precision-driven world of aerospace engineering, the universe refuses to conform neatly to our expectations. The pioneer anomaly underscores the sheer vastness of what we still do not understand, challenging our assumptions about how space behaves on the grand scale. As this unresolved mystery continues to intrigue researchers, it sets the stage for yet another cosmic oddity that resides at the very heart of our galaxy. With the next phase of the journey in sight, we delve into the mysterious heart of our galaxy, where an extraordinary force known as Sagittarius resides. This supermassive black hole, lurking right at the Milky Way's core, is a cosmic powerhouse with a mass equal to over 4 million suns. Despite its immense presence, it remains shrouded in mystery, defying many of our expectations about how black holes should behave. Unlike some black holes that voraciously consume surrounding matter, Sagittarius seems relatively quiet, only occasionally flaring up with bursts of energy when material gets too close. This subdued appetite puzzles researchers and raises compelling questions about what regulates its feeding habits. How does a force so powerful remain so seemingly dormant for extended periods? Furthermore, the conditions surrounding its formation remain a deep enigma. Did this colossal object grow gradually over billions of years, or did it emerge from a more dramatic and unknown event in the early universe? Even with cutting-edge telescopes and imaging techniques, observing Sagittarius is a monumental challenge due to its distance and the dense clouds of gas and dust that obscure it. Yet, when astronomers recently captured the first ever image of its event horizon, this breakthrough provided a tantalizing glimpse into the extreme physics governing these celestial bodies. Still, many questions linger. What causes its occasional dramatic flares? Could its peculiar behavior hint at unknown mechanisms in black hole dynamics? As we peer into this abyss, Sagittarius serves as a powerful reminder of the vast, untamed forces shaping the cosmos and how much we have yet to comprehend. From this enigmatic heart of the Milky Way, we now turn to a discovery that stretches across the universe itself, a structure so colossal it challenges the fundamental principles of cosmology. Moving forward, we encounter a cosmic marvel so immense that it redefines our understanding of scale itself, the Hercules Corona Borealis Great Wall. This is not just any structure in the universe, it is the largest known, stretching an astonishing 10 billion light-years across. To put that into perspective, light traveling at 186,000 miles per second would still take 10 billion years to traverse its expanse. This galactic supercluster comprises countless galaxies, each filled with billions of stars, all interconnected by a delicate filamentary web of dark matter and gas. Its sheer size is not just jaw-dropping. It is a direct challenge to one of the fundamental assumptions about our universe, the principle of universal homogeneity. This principle suggests that, on the largest scales, the universe should appear more or less uniform. In other words, no region of the cosmos should be drastically different from another when viewed broadly enough. The discovery of the Hercules Corona Borealis Great Wall disrupts this notion entirely. Its existence hints that the cosmos may not be as evenly distributed as once believed, raising profound questions about how such a massive structure could have formed. Current cosmological models struggle to explain how gravity alone could have gathered such a colossal assembly of matter in the relatively short history of the universe. Was its formation influenced by forces or processes we have yet to recognize? Or could it be evidence of physical principles operating on scales far beyond our current comprehension? Despite its overwhelming magnitude, the Hercules Corona Borealis Great Wall remains elusive, visible only through painstaking surveys of gamma-ray bursts, which reveal the cosmic geography of deep space. These bursts, the remnants of massive star explosions, act as distant beacons allowing astronomers to map such vast structures. Yet, the more we uncover about this great wall, the more questions arise about the universe's architecture and origins. Could this vast network of galaxies be part of an even larger, unseen pattern? Or is it a unique anomaly defying all logic? As we ponder the implications of this colossal discovery, we turn our attention to other fleeting, yet equally baffling celestial phenomena, ones that arrive in brief, powerful bursts and vanish as quickly as they come. Now turning to the next enigma of the cosmos, we find ourselves captivated by fast radio bursts, extraordinary flashes of radio waves that last mere milliseconds but pack as much energy as the sun emits in an entire day. These bursts, first discovered in 2007, have since left astronomers scratching their heads, as their origins remain one of the most perplexing questions in astrophysics. What we do know is that these bursts come from various points across the universe, with some emerging from galaxies billions of light years away. This means that they originate from immensely powerful events, but no single explanation has yet been able to account for all the observations. Some theories suggest that these bursts might result from cataclysmic occurrences, like the merging of neutron stars or the collapse of massive stars into black holes. Others propose that they could be linked to highly magnetized neutron stars called magnetars, whose intense magnetic fields could produce such energetic flashes. And then there are the more speculative ideas. Could these bursts be signals from advanced extraterrestrial civilizations attempting to communicate across vast cosmic distances? This possibility, while exciting, remains highly speculative and unproven. Adding to the mystery is the fact that most fast radio bursts are one-offs, never repeating. However, a handful of these bursts have been found to repeat from the same source, further complicating the puzzle. Scientists have observed these repeating bursts behaving differently from the one-offs, hinting at potentially diverse mechanisms behind them. To unlock the true nature of fast radio bursts, astronomers have turned to powerful radio telescopes, such as the Canadian Hydrogen Intensity Mapping Experiment, which has been pivotal in detecting these fleeting phenomena. Each new detection brings us closer to understanding their origin, yet also seems to deepen the mystery. Could these bursts be the result of exotic physics we have yet to uncover, or are they a natural part of the universe's complex symphony? Whatever the answer, fast radio bursts serve as a humbling reminder of how much we still have to learn about the cosmos. As we continue to search for clarity, we now shift our gaze toward an idea that challenges the very fabric of our understanding of the universe's nature and structure. Moving forward, we encounter a concept so astonishing it may forever alter how we perceive reality: the holographic principle. Imagine for a moment that everything around you, from the keyboard beneath your fingers to the stars scattered across the night sky, is not as it seems. This principle suggests that our three-dimensional universe might be a projection, much like a hologram, encoded on a two-dimensional surface at its boundaries. It is an idea rooted in the physics of black holes, where researchers discovered something extraordinary about how information is stored. In the 1970s, theoretical physicist Stephen Hawking revealed that black holes emit radiation, causing them to slowly lose mass over time, a process now known as Hawking radiation. But this presented a problem: what happens to the information contained in matter swallowed by a black hole? According to the laws of quantum mechanics, information cannot be destroyed, yet it seemed that black holes erased it from existence. This paradox puzzled scientists for decades. Then came a breakthrough. Physicists Leonard Susskind and Gerard T. Hooft proposed that the information falling into a black hole might not be lost but rather encoded on its event horizon, the two-dimensional boundary surrounding the black hole. This idea led to a more profound realization. If information about three-dimensional objects can be stored on a two-dimensional surface, could the entire universe operate under similar principles? Evidence supporting this theory comes from the study of cosmic phenomena and mathematical models, including string theory, which suggests that the fabric of our universe might indeed behave like a hologram. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, have hinted at patterns that align with the holographic model. If true, this would mean that our perception of depth and space is an illusion, akin to watching a three-dimensional movie projected on a screen. The implications of this are staggering, challenging the very foundations of physics and raising profound questions about the nature of existence. Are we living in a grand simulation, or is this simply a deeper layer of reality waiting to be understood? As scientists continue to probe the universe for answers, the holographic principle remains both a tantalizing mystery and a humbling reminder of how much we have yet to uncover. With this mind-bending idea swirling in our thoughts, let us turn now to one of the most fascinating objects in the cosmos, neutron stars, and their incredible, almost incomprehensible density. Now turning to one of the most awe-inspiring objects in the universe, neutron stars. These celestial remnants are born from the fiery deaths of massive stars left behind after supernova explosions. What makes them extraordinary is their unfathomable density. Imagine compressing the mass of 1.5 times our Sun into a sphere no larger than a city. To put this into perspective, just a single teaspoon of neutron star material would weigh billions of tons, more than the combined weight of every human on Earth. This staggering density is a result of the star's core collapsing under gravity so intense that protons and electrons merge into neutrons, creating what is essentially a gigantic atomic nucleus. But the marvel does not end there. Within this family of enigmatic stars, scientists have discovered some that push the limits of physics itself. Take, for example, the star known as J0740 plus 6620, the heaviest neutron star ever measured, with a mass about 2.5 times that of the Sun. Its very existence teeters on the brink of what physics predicts, challenging our understanding of matter at extreme pressures. Then there are magnetars, a rare type of neutron star with magnetic fields billions of times stronger than any magnet on Earth. These fields are so powerful that they can distort nearby atoms and even interfere with spacecraft electronics. And let's not forget pulsars, neutron stars that emit beams of radiation like cosmic lighthouses, spinning hundreds of times per second with mind-boggling precision. These stars defy what we thought was possible, existing at the edge of known physics. How can matter be compressed to such extremes without collapsing entirely? What strange states of matter might lie within their cores? Perhaps exotic particles like quarks or even unknown forms of matter. Neutron stars are not merely cosmic oddities, they are laboratories of extreme conditions, offering clues about the universe's most fundamental forces. As we continue our journey through the cosmos, the mysteries of neutron stars remind us that the universe is both a treasury of wonders and a humbling enigma. Now, as we delve deeper into the vast expanse of space, let us examine a discovery that truly bends the fabric of our understanding, the detection of particles in Antarctica that appear to move backward in time. Now turning to one of the most puzzling discoveries ever made on our own planet, the detection of particles in Antarctica that seem to defy the very flow of time itself. In 2016, scientists working with a high-altitude balloon equipped with the Antarctic Impulsive Transient Antenna, an experiment designed to detect cosmic rays, stumbled upon signals that could not be explained by known physics. Unlike normal high-energy particles that come from space and crash into the Earth's atmosphere, these particles appeared to be moving in the opposite direction, emerging from beneath the ice and traveling upward, as though they were rewinding through time. This bizarre observation has sparked debates and theories that stretch the limits of our understanding. Could these particles, known as neutrinos, be evidence of a mirror universe where time flows backward? Or could they point to entirely new physics that transcends the standard model? the framework scientists use to describe the fundamental forces and particles in our universe. Some suggest that this phenomenon might be tied to exotic concepts like time-symmetric theories or even interactions with alternate dimensions. If particles can truly behave this way, it raises profound questions about the arrow of time, the one-directional flow from past to future that we take as a given in our everyday lives. Does time itself have a hidden symmetry that we have yet to uncover? And if so, what might this mean for the origins and ultimate fate of the universe? While the Antarctic observations remain unconfirmed and controversial, they challenge us to explore the very boundaries of what we think is possible. As we continue to wrestle with these questions, the discovery serves as a powerful reminder that reality may be far stranger than we can currently comprehend. Moving forward, let us venture back into the depths of space to explore the elusive mystery of the missing baryon problem and what it means for our understanding of the universe's hidden matter. As the next challenge unfolds, we dive into the perplexing enigma known as the missing baryon problem. Baryons are the particles that make up the ordinary matter in the universe, forming everything we see around us, stars, planets, and even ourselves. According to cosmological models, scientists have calculated how much baryonic matter should exist since the universe's formation. Yet, puzzlingly, observations reveal that nearly half of this matter remains unaccounted for, as if it's vanished into thin air. This discrepancy has left astronomers scratching their heads for decades. Where could this missing matter be hiding? To solve the mystery, researchers have turned their attention to the vast intergalactic spaces between galaxies, suspecting that the baryons might be dispersed in an incredibly diffuse and hard-to-detect form. Some studies point towards the warm-hot intergalactic medium, a faint web of gas spread across the cosmos as a possible hiding place. This gas is so tenuous that it barely emits detectable light or radiation, making it extraordinarily difficult to pinpoint. Innovative techniques using X-rays from distant quasars have provided tantalizing hints that the missing baryons could indeed be lurking in this elusive medium. If confirmed, this would not only solve one of the great riddles of modern cosmology, but also deepen our understanding of how matter is distributed on the grandest scales. However, if these baryons remain undiscovered, it might suggest that our models of cosmic matter are incomplete, urging us to rethink the very frameworks we rely on to describe the universe. The missing baryon problem exemplifies the tantalizing gaps in our knowledge, reminding us that even the most fundamental questions about the cosmos often come with no easy answers. As we continue our journey, let us now shift our focus to another cosmic oddity, the rogue planets that defy the traditional rules of planetary formation. With the next phase of the journey in sight, we encounter the mysterious rogue planets, lonely wanderers adrift in the vast darkness of interstellar space, unbound by the gravitational pull of any parent star. Unlike typical planets that form and orbit within the nurturing environment of solar systems, rogue planets exist entirely on their own, floating through the galactic void. Their existence defies the conventional rules of planetary formation, leaving scientists to wonder how such solitary worlds came to be. One theory suggests that these planets might have originally formed within star systems, just like Earth or Jupiter, but were later ejected by gravitational interactions with larger objects, such as massive gas giants or even passing stars. Another possibility is that some rogue planets could form directly from collapsing clouds of gas and dust, much like miniature stars, but fail to ignite nuclear fusion due to their smaller size. What makes these planetary nomads even more fascinating is their potential resilience. Without the warmth and light of a star, rogue planets would appear to be barren, frozen worlds. However, some researchers speculate that certain rogue planets, particularly those with thick atmospheres or subsurface oceans heated by radioactive decay, could harbor conditions suitable for life even in the cold void of space. Observing these elusive objects is no easy feat, as they emit little to no visible light and are often detected indirectly through methods like gravitational microlensing, where their presence temporarily warps the light from background stars. The discovery of rogue planets challenges our understanding of how planets form, evolve, and survive, pushing us to rethink our most basic assumptions about planetary systems. As we ponder these wandering worlds, we now set our sights on another unexplained phenomenon, the dark flow, an enigmatic motion of galaxy clusters that hints at the influence of something far beyond the observable universe. With the next phase of the journey in sight, we delve into the perplexing phenomenon known as the dark flow, a cosmic mystery that has left scientists grappling for answers. Imagine gigantic clusters of galaxies, each containing countless stars, planets, and potentially life itself, all inexplicably moving in the same direction at astonishing speeds. This motion is not random. It seems to align toward a specific region of the sky, as if an unseen force is pulling them from beyond the boundaries of the observable universe. The question that baffles researchers is, what could possibly exert such an immense influence over these galactic clusters? One theory suggests that this motion could be caused by massive structures lying outside the detectable range of our telescopes, remnants of the early universe that predate the formation of galaxies as we know them. These structures, too far away for their light to have reached us, might still be shaping the motion of matter on a cosmic scale. Another possibility is even more mind-bending: the existence of another universe or dimensions beyond our own, whose gravitational pull leaks into our universe and nudges these galaxies along their mysterious paths. Whatever the cause, the dark flow phenomenon challenges the very foundations of cosmology, forcing scientists to rethink the limits of what we can observe and understand. Measurements from cosmic microwave background radiation have hinted at this anomalous motion, but so far, the data only scratches the surface of what remains a deeply confounding puzzle. As we turn our attention to the next enigma in our cosmic voyage, we encounter the curious Kuiper Cliff, a puzzling drop-off in the number of celestial objects in the distant reaches of our solar system, defying expectations and raising even more questions about the structure of the cosmos. Now turning to the Kuiper Cliff, we encounter a baffling phenomenon at the very edge of our solar system. Imagine the Kuiper Belt, a vast region of icy objects orbiting beyond Neptune, filled with remnants from the early days of planetary formation. It was once thought to be a relatively uniform distribution of these frozen worlds, extending far into the outer reaches of our solar system. However, past a certain distance, roughly 50 times farther from the Sun than the Earth, there is a dramatic and unexpected drop-off in the number of detected objects. This sudden scarcity has been named the Kuiper Cliff, and it presents an enigma that has left astronomers searching for answers. What could cause this sharp boundary? One theory suggests that a massive and as yet undiscovered planet, often referred to as Planet 9, could be lurking in the shadows, its gravitational influence clearing out objects beyond this point. Another possibility is that the edge of the Kuiper Belt marks a natural limit in the solar system's formation process, where conditions were no longer favorable for icy bodies to coalesce. Some researchers even propose that external forces, such as tidal disruptions from a passing star billions of years ago or the gravitational pull of the Milky Way itself, might have shaped this peculiar edge. Despite advancements in technology, the Kuiper Cliff remains a cosmic question mark, as no definitive explanation has yet emerged. Its abrupt nature challenges our understanding of the solar system's structure and formation, reminding us just how much remains unknown in the vastness beyond our familiar worlds. Looking ahead, our journey takes us even deeper into the mysteries of the cosmos, venturing into the mind-bending concept of the multiverse, where our universe may be just one of countless others coexisting in an unfathomable cosmic expanse. Moving forward, we step into one of the most mind-boggling concepts in modern science, the multiverse theory. Imagine for a moment that our universe, vast and infinite as it seems, might actually be just one of countless others. This idea suggests that beyond the boundaries of what we can observe lies a cosmic expanse filled with parallel universes, each potentially governed by its own unique laws of physics. What gives this theory weight is not just imagination but emerging scientific evidence. For example, certain patterns in the cosmic microwave background radiation, often described as the afterglow of the Big Bang, hint at the possibility of interactions between our universe and others. Additionally, some interpretations of quantum mechanics, particularly those involving the many worlds theory, propose that every decision or event creates a branching timeline, spawning new universes in the process. While these ideas spark fascination, they also raise staggering questions. Could there be another version of you, living a different life in a parallel world? What would it mean if these alternate realities could interact with our own? The implications of the multiverse stretch beyond comprehension, challenging our understanding of existence itself. It defies logic to think that our reality may be just a tiny sliver of a much larger, infinitely complex system. Yet no definitive proof exists, at least not yet. As researchers probe deeper, using advanced simulations and experiments like those conducted at particle accelerators, they inch closer to unlocking the secrets of this daring hypothesis. For now, the multiverse theory remains a tantalizing mystery, one that pushes the boundaries of science and imagination alike. And as we ponder the infinite possibilities, our next stop takes us to a phenomenon that showcases the extraordinary forces within our own galaxy. The discovery of hypervelocity stars streaking across the cosmos at breathtaking speeds. With the next phase of the journey in sight, let us uncover the phenomenon of hypervelocity stars, celestial objects that defy all expectations by racing through our galaxy at speeds of tens of millions of miles per hour. These stars are not your ordinary cosmic neighbors. They hurtle across the universe with velocities so extreme that they can escape the gravitational pull of the Milky Way entirely. But how do these stellar speedsters achieve such astonishing velocities? Scientists believe that hypervelocity stars are often the result of dramatic, high-energy events. One leading theory involves interactions with supermassive black holes, like the one residing at the center of our galaxy, Sagittarius A. Imagine a binary star system, a pair of stars orbiting each other, drifting too close to the immense gravitational force of a black hole. The black hole's incredible pull could rip the pair apart, swallowing one star while slingshotting the other outward at breathtaking speeds. Another possibility is that these stars are the remnants of supernova explosions, where the force of the blast ejects the star at incredible velocities. The discovery of hypervelocity stars not only showcases these extraordinary cosmic forces, but also serves as a unique tool for astronomers to map the galaxy. By tracking their trajectories, scientists can gain insights into the shape, structure, and gravitational dynamics of the Milky Way. These stars are like cosmic breadcrumbs, tracing paths that reveal the invisible influences shaping their motion. Yet, even with these theories, questions remain. How often do such events occur, and could there be other mechanisms propelling stars to such speeds? These mysteries add another layer of intrigue to the study of hypervelocity stars. As we follow their journey across the cosmos, they remind us of the immense power and complexity at play in our galaxy. Now turning to the next chapter, we venture into the story of a galaxy that stands completely alone in the vast emptiness, defying the very idea of cosmic companionship. Now turning to the next chapter, we venture into the desolate and mysterious realm of MCG plus 01020015, often referred to as the loneliest galaxy. Imagine a galaxy adrift in the vast cosmic ocean with no neighbors in sight, millions of light years away from any other cluster of stars or galaxies. MCG plus 01020015 defies the very concept of cosmic community, standing utterly isolated in the infinite expanse of space. But how did it end up in such profound loneliness? One prevailing theory suggests that this galaxy may have formed in a region of the universe that is exceptionally devoid of matter, a true cosmic void. These voids are vast, empty regions of the universe where the density of galaxies and other cosmic structures is significantly lower than average. While most galaxies form within clusters or along the intricate filaments of the cosmic web, MCG plus 01020015 appears to have been left behind, far from the gravitational pull of any larger structures. Another possibility is that this galaxy was once part of a galactic group or cluster, but was flung into isolation through interactions with other massive galaxies. Such gravitational encounters could strip it of its companions and send it adrift into the lonely depths of the universe. The mysteries surrounding MCG plus 01020015 are not just about its origins, but also its survival. Isolated galaxies like this often lack fresh supplies of gas, the essential ingredient for star formation. Yet somehow, this galaxy has managed to persist and maintain its structure in the face of cosmic solitude. For astronomers, the study of such isolated galaxies provides insights into both the extreme conditions under which galaxies can survive and the larger dynamics that govern their interactions and evolution. What secrets might MCG plus 01020015 hold about the universe's formative years, and what can its isolation teach us about the cosmic forces at play? As we ponder these questions, the loneliest galaxy reminds us of the profound diversity and unpredictability of the cosmos. Moving forward, let us dive into the next enigma, a star system where an exoplanet defies all logic by orbiting in complete opposition to its star's rotation. Moving forward, we find ourselves captivated by the intriguing Beta Pictoris system, a stellar system that has left astronomers both baffled and fascinated. At the heart of this cosmic puzzle lies a giant exoplanet, an enormous world whose orbit defies the natural order we have come to expect. This planet, known as Beta Pictoris b, moves in a direction completely opposite to the rotation of its parent star. To put this into perspective, imagine throwing a ball that inexplicably curves against the spin of the Earth beneath it. This is the kind of anomaly we are witnessing on a planetary scale. Typically, planets form from a swirling disk of gas and dust that revolves in the same direction as the star it surrounds, leading to an alignment known as prograde motion. This is a foundational concept in planetary formation, making the retrograde orbit of Beta Pictoris be a serious challenge to our understanding of how planets and solar systems come to be. Theories have emerged in an attempt to explain this puzzling behavior. One possibility is a giant cosmic collision in the system's past, where an encounter with another massive object could have disrupted the planet's orbit, causing it to reverse its direction. Another scenario suggests that gravitational interactions with a nearby companion star or planet may have forced Beta Pictoris b into its current trajectory, though such interactions on this scale remain difficult to prove. This retrograde motion raises deeper questions about the stability and evolution of planetary systems. Could such chaotic beginnings be more common than we think, hidden in the vastness of the cosmos? Or are we looking at an exceptionally rare occurrence that pushes the limits of what is possible? Whatever the case, the Beta Pictoris system reminds us that the universe is not limited by our expectations or assumptions. It is a testament to the fact that even as we learn more about planetary formation, there are always new mysteries waiting to challenge what we think we know. As we leave this perplexing system behind, our journey now takes us to another awe-inspiring cosmic phenomenon, where black holes unleash energy in ways that seem to defy all comprehension. As the next challenge unfolds, we journey into the enigmatic realm of black holes and their awe-inspiring relativistic jets. These jets are colossal streams of energy and matter that black holes eject at speeds approaching that of light itself. Imagine a force so powerful that it can launch particles across vast intergalactic distances, creating beams that stretch for hundreds of thousands of light years. This extraordinary phenomenon occurs when a black hole, often thought of as a cosmic vacuum, paradoxically becomes a source of immense outward energy. But how can an object known for pulling everything inward, even light, emit such staggering jets in the opposite direction? This paradox lies at the heart of the mystery surrounding black holes. Scientists believe that these jets are related to the accretion disk, a swirling halo of superheated gas and dust spiraling into the black hole. As this material falls inward, it generates intense magnetic fields and friction, converting gravitational energy into the powerful bursts we see. Yet, the exact mechanism through which these streams are accelerated and focused to such extreme speeds remains one of the greatest unsolved puzzles in astrophysics. Adding to the complexity is the fact that not all black holes produce relativistic jets, and why some do while others remain silent is still unclear. Could it depend on the black hole's spin, the composition of its accretion disk, or some unknown factor we have yet to uncover? These jets also challenge our understanding of the stability of spacetime itself. Traveling at nearly the speed of light, they serve as natural laboratories for studying the effects of extreme relativity, where the rules of physics as we know them begin to stretch and break. The immense energy they release has far-reaching implications, influencing the formation of galaxies and spreading elements essential for life across the cosmos. At their core, relativistic jets are a testament to the universe's ability to defy logical expectations, forcing us to reconsider what we know about black holes and the forces they unleash. With the next phase of the journey in sight, we turn our gaze to the web-like structure of the universe itself, where galaxies are connected in a way that seems both chaotic and uncannily orderly. With the next phase of the journey in sight, we delve into the fascinating concept of the cosmic web, an intricate yet seemingly delicate structure that binds the universe together on its largest scales. Picture a spider's web stretching across unimaginable distances, where each strand represents vast clusters of galaxies, interconnected by filaments of gas, dark matter, and gravitational forces. This sprawling network forms the very skeleton of the universe, with nodes where galaxies gather and empty voids spanning the spaces in between. But how did such a remarkably organized pattern emerge from the chaotic aftermath of the Big Bang? Scientists theorize that the cosmic web came into existence as gravity began to pull matter together over billions of years, shaping the universe into this vast, interconnected structure. Dark matter, the elusive substance that makes up most of the universe's mass, plays a critical role here, acting like an invisible blueprint guiding the formation of this intricate network. Yet the symmetry and order of the cosmic web defy simple explanations. Why does it appear so uniformly distributed when the universe itself has undergone such tumultuous evolution? What mechanisms ensure such balance in the grand cosmic design? Studying the cosmic web also reveals clues about the universe's mysterious expansion, showing how galaxies move along these filaments under the influence of forces we are only beginning to understand. Even more intriguingly, the cosmic web serves as a bridge between the largest observable structures and the subatomic world, offering tantalizing insights into the fundamental nature of reality. This vast network challenges our understanding of chaos and order on a universal scale, leaving us to ponder whether there is a deeper design or principle at work in the cosmos. With these questions hanging in the void, we now turn our attention to one of the universe's most perplexing discoveries, a star that appears to defy the very age of the universe itself. Now turning to the Methuselah star, a discovery that seemingly defies both logic and the very fabric of cosmic chronology. Officially known as HD 140283, this peculiar star resides in our Milky Way galaxy, approximately 200 light-years away from Earth. What makes it truly astounding is its estimated age, roughly 14.5 billion years. To put this into perspective, the age of the universe itself is calculated to be about 13.8 billion years. This presents a fascinating contradiction. How could a star be older than the universe in which it exists? Scientists have grappled with this paradox, and while several theories attempt to reconcile the discrepancy, none provide a definitive answer. One possibility is that errors in measuring either the star's age or the universe's age might be at play. However, even with advanced techniques and refined calculations, the Methuselah star consistently appears to be staggeringly ancient. This star's unique characteristics, such as its extremely low metal content, further reinforce its status as a relic from the universe's infancy. In stellar astronomy, metals refer to elements heavier than hydrogen and helium, and their scarcity in this star suggests it formed from primordial materials shortly after the Big Bang. The Methuselah star challenges our understanding of stellar evolution, cosmic timelines, and even the models we use to estimate the age of the universe. Could it be that our calculations about the universe's age are incomplete? Or does this star hold clues to phenomena beyond our current comprehension? The Methuselah star reminds us that the cosmos might still hide fundamental truths about its origins, waiting to be unveiled. With this enigma lingering in the depths of space, we now shift our focus to another marvel that reshapes our understanding of life's potential in our solar system: the breathtaking plumes of water erupting from Saturn's icy moon, Enceladus. Now turning to the compelling wonder of Enceladus, Saturn's icy moon offers a spectacle that has fascinated scientists and dreamers alike. Towering plumes of water erupting through its frozen surface and shooting into space. These geysers were first detected in the early 21st century by the Cassini spacecraft, revealing that Enceladus is far more than just an ordinary celestial body. Beneath its thick crust of ice lies a vast subsurface ocean, warmed by geothermal activity. What makes this discovery even more extraordinary is the detection of organic compounds within the expelled material, the chemical building blocks of life as we know it. These compounds, combined with the presence of liquid water and the moon's internal heat, create conditions that are remarkably similar to those thought to have given rise to life on Earth. Could Enceladus harbor microbial life in its hidden ocean, swimming in the dark warmth beneath layers of ice? Or are these organic signatures merely the byproducts of non-biological processes? Either way, the plumes of Enceladus have transformed it into one of the most promising locations in our solar system for the search for extraterrestrial life. This icy moon challenges not only our understanding of where life might exist, but also how resilient and adaptable life could be in environments previously thought too extreme. As technology advances and missions to further explore this fascinating moon are planned, one can only wonder what secrets might still be trapped beneath its glistening, frozen surface. With our imaginations sparked by the possibility of life beyond Earth, let us now explore a theory that forces us to look inward at the challenges of existence itself, the enigmatic concept known as the Great Filter hypothesis. Moving forward, we come to the profound and unsettling concept of the Great Filter hypothesis. This theory suggests that somewhere along the path from simple life forms to advanced spacefaring civilizations, there exists a nearly insurmountable barrier. This so-called filter could be behind us, such as the leap from non-living chemicals to life itself, or it could lie ahead in the form of challenges that threaten the survival of technologically advanced societies. If the Great Filter is in our past, humanity may be one of the very few, or perhaps the only, intelligent civilization to have overcome it. However, if it still lies ahead, it raises sobering questions about our long-term prospects. Could it be environmental collapse, nuclear catastrophe, or some unforeseen challenge that ends humanity's progression? The implications of this idea are staggering. It shifts our search for extraterrestrial life into a more existential reflection. If we find no evidence of other advanced civilizations, it might be a sign that life rarely makes it past the filter, and we may have already succeeded where others have failed. Conversely, if we detect advanced life elsewhere, it could signify that the most daunting challenges are still to come for us. This paradox leaves us wrestling with optimism and caution while peering into the unknown. By confronting the Great Filter hypothesis, we not only explore our place in the cosmos, but also gain a deeper understanding of the precarious journey we are on as a species. Contemplating these challenges, let us now venture into the mysterious void that further defies our expectations of space, the enigmatic and vast Boötes void. Now turning to the Boötes void, we encounter one of the most baffling cosmic structures ever discovered. This colossal region of space stretches over 330 million light-years across and is strikingly empty, hosting far fewer galaxies than expected for an area of its size. To put this into perspective, in most regions of the universe, galaxies are scattered relatively uniformly, like stars sprinkled across the sky. Yet within the Boötes void, there appears to be an immense, gaping absence. This has led scientists to dub it one of the largest known voids in the cosmos, a title that only adds to its mystique. Theories about how this massive emptiness came to be are as elusive as the void itself. Some suggest that it formed through the cosmic evolution of matter, where regions of the universe naturally clump together into dense areas, leaving behind vast, empty pockets. Others propose that smaller voids merged over billions of years, eventually shaping the Boötes void into the enormous enigma we see today. But even these ideas struggle to fully account for its staggering scale and near-total emptiness. The void's very existence challenges our understanding of cosmology, which assumes that the universe should be relatively uniform on large scales. Why would such a significant anomaly exist in a cosmos that otherwise exhibits remarkable balance and order? This question continues to puzzle scientists and fuels an ongoing search for answers. Could we be missing a fundamental piece of the puzzle when it comes to how the universe is structured? Or could this void point to phenomena we have yet to comprehend, such as the influence of dark energy or forces beyond our observable horizon? What makes the Boötes void even more fascinating is how it forces us to reconsider our assumptions about the universe's composition and history. It serves as a humbling reminder of how much we still have to learn about the cosmos. With this, our journey through the extraordinary and puzzling aspects of space leads us to yet another profound question about the universe's ultimate mysteries, the strange and long-standing puzzle of antimatter's scarcity. Moving forward, we encounter the perplexing antimatter mystery, a cosmic puzzle that strikes at the very foundation of our understanding of the universe. According to widely accepted theories, the Big Bang should have produced equal amounts of matter and antimatter. For every particle of matter, there should have been a corresponding particle of antimatter. When matter and antimatter meet, they annihilate each other, releasing pure energy. So, if the amounts were equal, why does our universe exist primarily as matter, while antimatter is almost nowhere to be found? This question has puzzled scientists for decades and has sparked countless experiments and theories. One of the most promising areas of investigation centers on the possibility that matter and antimatter do not behave in exactly the same way. This idea, known as charge parity violation, suggests that subtle differences in their behavior could have tipped the scales in favor of matter during the universe's earliest moments. Scientists have been probing this hypothesis through experiments using powerful particle accelerators like the Large Hadron Collider. By smashing particles together at immense speeds, researchers aim to recreate the conditions of the early universe and examine the minute details of matter-antimatter interactions. These experiments have yielded tantalizing hints of asymmetries, but not enough to fully explain the overwhelming dominance of matter. Another intriguing possibility involves processes that might have occurred during cosmic inflation, a period of rapid expansion immediately after the Big Bang. Some scientists theorize that this inflationary phase could have amplified the tiny differences between matter and antimatter, leading to the imbalance we observe today. Yet, despite decades of exploration, no single theory has provided a definitive answer to this towering question. The scarcity of antimatter remains a cosmic enigma, one that challenges our most fundamental principles of physics and cosmology. What is even more fascinating about this mystery is its practical implications. If we could better understand antimatter, it could revolutionize energy production and even space travel. Antimatter is the most efficient energy source known, as seen in its total annihilation with matter. However, because it is so rare, producing and storing antimatter remains one of the greatest technological challenges of our time. Scientists at facilities like CERN are not only investigating the origins of antimatter, but also trying to learn how to harness it for practical use. The antimatter mystery does more than just highlight a theoretical imbalance in the universe. It forces us to confront the limits of our knowledge and the possibility that the answers we seek may lie in concepts or dimensions that we have yet to uncover. Could the solution to this cosmic conundrum be hidden in the way the universe operates on a quantum level, or does it point to phenomena beyond the scope of current physics? As we ponder these questions, we move forward into yet another intriguing chapter of cosmic discovery, the perplexing patterns of cosmic alignments that seem to defy chance and hint at hidden forces shaping our universe. As the next challenge unfolds, we delve into the curious phenomenon known as the cosmic alignment problem, a riddle that seems to defy reason and probability. Imagine vast structures in the universe spanning billions of light years, exhibiting alignments so precise that they appear to mock the randomness of cosmic formation. This mystery becomes particularly intriguing when we examine phenomena like the alignment of quasar polarizations or the strange patterning of cosmic microwave background radiation. These alignments are not just subtle coincidences, they suggest an underlying order to the cosmos that challenges our current models of cosmology. One of the most compelling examples of this enigma is the alignment of the so-called axis of evil. Scientists discovered that certain fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, appear to align along a specific axis when mapped out. This axis intriguingly corresponds to the plane of our own solar system, an observation that raises eyebrows and deep questions. How could such a large-scale cosmic feature be aligned with something as locally specific as our solar system? It seems highly improbable, and yet the data persist. Another puzzling case comes from the study of quasars, those incredibly bright and distant objects powered by supermassive black holes. Observations have revealed that the polarizations of light emitted by certain quasars are strangely aligned across vast distances of space, sometimes spanning billions of light years. This degree of alignment defies expectations, as the universe is generally assumed to be isotropic, meaning it should appear the same in all directions at such scales. These findings hint at the possibility of hidden forces or mechanisms shaping the universe in ways we do not yet comprehend. The cosmic alignment problem forces scientists to confront profound questions about the origins of the universe and the principles governing its structure. Could these alignments point to some kind of cosmic blueprint, an unseen framework that influenced the formation of galaxies and large-scale structures? Or could they be evidence of phenomena as yet undiscovered, possibly originating from forces or dimensions beyond our observable universe? Some researchers even speculate that these alignments could hint at the existence of multiverses, with overlapping realities subtly influencing each other. Despite the efforts of countless astronomers and physicists, the cosmic alignment problem remains unsolved. It challenges our foundational assumptions about the nature of the cosmos, urging us to rethink the principles of randomness and order on the grandest of scales. This enigma reminds us that for all our progress in understanding the universe, many of its deeper mysteries remain shrouded in the unknown, waiting for future discoveries to shed light. As we ponder the hidden forces and possibilities raised by these alignments, we now turn to a groundbreaking achievement in modern astronomy, the shadow of the black hole, a momentous leap in unraveling the secrets of the cosmos. Now turning to a moment that truly represents a monumental leap in our exploration of the cosmos, we examine the shadow of the black hole, a discovery that shook the very foundations of astrophysics. In the year 2019, humanity achieved what seemed like an impossible feat, capturing the first direct image of a black hole's shadow. This extraordinary accomplishment was made possible through the Event Horizon Telescope, a global collaboration of radio observatories that worked together to create an Earth-sized virtual telescope. The target of this ambitious project was a supermassive black hole located in the center of the galaxy Messier 87, roughly 55 million light-years away from us. The result, a glowing, ring-like structure surrounding a dark central region, an image that confirmed theoretical predictions of what a black hole's shadow should look like based on Einstein's theory of general relativity. But why was this image so important, and what does it tell us? First, it provided visual, observational evidence of black holes, objects that had long been theorized but never directly observed in this way. The shadow itself is not the black hole per se, but the silhouette created by the bending of light around its event horizon, the outer boundary beyond which nothing, not even light, can escape. This image confirmed our understanding of the extreme warping of spacetime caused by a black hole's immense gravity. It also validated decades of theoretical work in physics and astronomy, further cementing Einstein's legacy as one of the greatest scientific minds in history. However, obtaining this image was no small task. The Event Horizon Telescope required unprecedented coordination across continents, with observatories positioned from Antarctica to Spain and from Chile to Hawaii. Massive amounts of data, equivalent to thousands of hard drives, were collected and processed using state-of-the-art algorithms to produce the iconic image. Adding to the challenge, the black hole itself is surrounded by turbulent plasma emitting radio waves, making it even more difficult to distinguish its shadow from the surrounding noise. The sheer precision and ingenuity required to overcome these hurdles speak volumes about human determination and the power of collaborative science. Yet, for all its triumphs, this discovery only deepens the mystery surrounding black holes. What lies beyond the event horizon? Are black holes gateways to other dimensions or universes, as some theories suggest? How do they grow and interact with their surroundings, influencing the evolution of galaxies? The shadow of the black hole is a tantalizing clue, but it raises far more questions than it answers. It challenges us to dig deeper into the unknown, to push the boundaries of our technology and imagination in search of answers. As we marvel at this groundbreaking achievement, we are reminded that black holes are not merely cosmic phenomena to be studied from a distance. They are keys to understanding the fundamental nature of reality itself, from the mechanics of space-time to the origins of the universe. This awe-inspiring image serves as a testament to human curiosity and the unending quest to uncover the secrets of the cosmos, leaving us to wonder what other astounding discoveries await just beyond the horizon. As we bring our journey through these 30 cosmic discoveries to a close, one thing becomes abundantly clear. The universe is far more enigmatic, intricate, and awe-inspiring than we could ever imagine. Each of these discoveries, from the Great Attractor's mysterious pull to the shadow of the black hole, has challenged our understanding of reality and pushed the boundaries of science, opening doors to countless questions that remain unanswered. These findings remind us that no matter how much we learn, the cosmos still holds secrets that defy logic, waiting to be uncovered by future explorers, dreamers, and thinkers. From the warped fabric of space-time around black holes to the tantalizing hints of alternate universes, these mysteries not only enrich our knowledge but also fuel our imagination, inspiring us to reach beyond the limits of the known. What lies beyond the cosmic web? Could rogue planets harbor unknown forms of life? Is our universe just one of many? These are questions that compel us to keep looking upward, to keep questioning, and to keep wondering. As we continue this journey together, let us celebrate the remarkable achievements of human curiosity and determination that have brought us this far. If any of these discoveries left you amazed, puzzled, or eager to learn more, we'd love to hear your thoughts. Which of these cosmic mysteries captured your imagination the most? Be sure to share your insights in the comments below. And if you enjoyed unraveling these wonders of the universe with us, don't forget to like the video, hit the subscribe button, and turn on notifications so you never miss an opportunity to explore the unknown. Remember, in the vastness of space, every answer we find leads to even greater questions, and it is this very pursuit of the unknown that unites us in wonder. Thank you for joining us on this incredible journey through the cosmos. Until next time, keep your eyes on the stars and your mind open to the infinite possibilities that await.